Okay, I'm going to look at problem 14-54. Okay, this is we have a car and it has a defined mass, 2.3 megagrams, and it's accelerating at a constant, has a constant acceleration of 6 meters per second squares, and it's per second squared, and it's starting from rest. Okay. Now, we have a defined drag resistance on the car due to the wind, and that's equal to, it's a function of velocity. It's basically equal to 10 times whatever the velocity is at that point in time. And v is defined in velocity as meters per second. We need to determine the power supplied to the engine when t is equal to 5 seconds. Okay? So what we need to do is we have a certain drag that's a function of velocity, and velocity is a function of time. So at 5 seconds, whatever the velocity is, that will give us the drag force. Okay? Okay. So for certain things to start off with, we have our, we're looking for power at t equal to 5 seconds. We're given the mass of the car, which we need to convert to kilograms. Um, then we have our acceleration, which is a constant, defined as 6 meters per second squared. We have our force, drag force, which is 10 times the velocity. Okay. And then we have our efficiency. All right. So in terms of our governing equations, right off the bat, we have our equation for motion, we have our efficiency, and then we have our power output. So we know we're going to need these. Well, the only other thing is that since our uh, force, drag force, as a function of velocity, we're going to need to have also find out what our velocity is at that point in time. So we're going to need our kinematic equation for velocity. Okay. So first thing is we're going to apply our equation of motion. And when we do that, sorry, one more thing before that. Free body diagram, right? We have a free body diagram, and so these are the forces. We have a force of drag acting against the car. We have a force of the engine pushing it forward. And that's going to, and we also have weight and a normal force, which we're not going to need because we don't have any friction, rolling friction in this problem. And that's going to equal our mass times our acceleration. Okay, so here's our kinetic diagram, our free body diagram and our kinetic diagram. Okay, so we apply the equation of motion. So we have summation of the forces in the x direction equal to the mass times the acceleration of x. Okay, well, in the x direction we found it was force of the engine pushing the car forward and the force of drag against it. And that's going to equal the mass times acceleration in that direction. Okay, so we just substitute in for our force and our mass. This is actually, we actually do know what this is. This is the 6 meters per second squared here. Although I didn't put it in here, I'll put it in later. But in this case, we still don't know what the velocity is, right? We can't find that force until we know what the velocity is, okay? And that's where we can use our kinematic equation to solve for it, all right? So here's our kinematic equation. And what we know is that it started from rest, so v initial 0, and our acceleration, 6 meters per second squared, times 5 seconds gives us our 30 meters per second, right? Because we care about that velocity at 5 seconds, okay? Okay, and now what we can do is use our power output equation, which is just essentially the dot product of force with the velocity in that direction, right? So it's, well, it gives you that direction. Essentially, the dot product is a projection, right, onto each vector. So this would be like the only component really that's left is the x component, right, in the x direction. So I have my force in the x direction, okay, which was what we previously had. We put in the 13.8 um, and then times 10.3 and then um, okay, just continuing on. I forgot to write down that force equals ma plus 10v. So this was the part that we had previously found from that our kinetic equation, our equation of motion. We just rearrange it and we take 10v from one side and put it on the other side of the equation. And so here it is. We know what ax is, which is our constant acceleration, and we know what m is, and that's essentially this. And here's our 10v because we found our velocity. Okay. This was our 6 meters per second squared, and this was our mass. Okay, that we had defined. Okay, so now we do the dot product. Here's our velocity, our 30 meters per second, and then we come up with 423 kilowatts. So the last step, of course, is just solving for our input power, which is just going to be equal to our output power. This is PO divided by epsilon equals 622 kilowatts. So P output was this. Epsilon was our value that we were given for the problem, 0.68. And then we solve for that. And that's it.